All right, so thank you everyone for joining us for this global Poisson webinar. On behalf of my co-organizers and the Zoom master, Nikita, I want to thank Rui for agreeing to give the first talk. All right, okay. So Rui will give the first talk. His talk is about local models around Poisson submanifolds.
All right. Okay. Hi, everyone. Hope you are all safe. Unfortunately, that's the first thing nowadays we start our conversations with. Going through some incredible period of time. I think these days having a job, feeling healthy, and having your loved one healthy is already like, you feel already very blessed. And there is so much suffering going around, and people sacrificing also themselves. That it's just amazing. Anyway, so I'd like to thank the organizers for taking this initiative. It doesn't quite replace the joy of seeing each of you every summer, but still it's great. Thanks for the invitation to give the talk. I was joking with Anton, for those who arrived late, that you give this talk and then you cannot go around and give the same talk anymore because everyone with such a global audience have already seen you talk about that. And also jokes don't quite work here, so I will stop trying to make jokes because you don't see anyone laughing, so you feel that it's always a bad joke. So anyway, let's start. So this is based on the work I want to report today is based on joint work with Johan Marcoux. It's not published or preprint form yet. It's really about a very classical question in Poisson geometry. So we have our Poisson manifolds, and we have a closed Poisson submanifold. And we are asking about the existence of a first order local model around this submanifold. So when you first see this question, maybe you feel a little bit weird because you are used to situations where usually there is a local model. But as we will see later, that's actually not always the case here. So that's actually the very first question in this problem is the existence of local models. Now, assuming that such a local model exists, you can ask if it is a normal form, whether if I have some Poisson manifold whose first order data coincides with your local model, whether it's local isomorphic to the local model. So can you linearize your Poisson structure around this Poisson submanifold? And a related problem with the linearization problem is the rigidity problem. So the rigidity problem asks you if I have two Poisson structures whose first order data coincides along this submanifold, whether they are locally isomorphic. So in our work, we have answers to these questions. And so the first theorem is about the existence. And we will see that a certain class of first order jets, I will have to explain what that means, satisfying the so-called partial splitting condition, admits a first order local model. So in your situations that you are most familiar with, so say if you have a zero of a Poisson structure, or if you have a symplectic leaf of a Poisson structure, these first order local models always exist. And in fact, in that case, your first order jet is always admits a partial splitting. So it satisfies this partial splitting condition. However, there are situations that we'll see where such a condition is not satisfied, and even more, there are situations where we don't have a local model. The second result is a very general linearization result that says that if we have a Poisson manifold whose first order jet, which is in some sense codified by the restriction of the cotangent algebroid to this submanifold. So if this restriction is integrable by a compact Lie groupoid, whose source fibers have trivial second de Rham cohomology, then you can linearize your Poisson structure around this Poisson submanifold. And out of this result, you would get as a corollary the most general result up to date, which is a result to Marcoux from 2014, that it's not about linearization, but it's about rigidity. So this result says that under the same assumptions of the theorem that I just quoted, if I have two Poisson structures that coincide, or whose first jet coincide along these Poisson submanifolds, then they are locally isomorphic. Now, one of the issues that in the work of Marcoux was that he didn't have a local model, and so he could only state it's such a rigidity result. So we'll come back to this question of linearization versus rigidity later. Now, our approach, and really the reason why we got into the existence and to understand why such a first order local model exists, our approach came from looking from this problem from a global perspective. So from the perspective of groupoids. So let's go discuss that a little bit, because there are also some results there which are interesting. So suppose I have a symplectic groupoid. So remember, that means we have a closed to form, which is multiplicative and which is symplectic, so it's non-degenerate. And there is also a concept of an oversymplectic groupoid. So there you relax the condition of the form being symplectic, but you require a condition on the kernel, so the kernel must be contained in the isotropy, or in the tangent to the isotropy. So in the intersection of the kernel of the source and the kernel of the target. So this term oversymplectic, I will explain it later. So this comes from the work of Burstein, Kreinig, Weinstein, and Zhu, and we'll come back to that later. So the first, why oversymplectic groupoids play a role here is that if I start with a symplectic groupoid and I restrict it to a saturated submanifold, meaning a manifold which is a union of orbits, then the restriction is an oversymplectic groupoid. Moreover, the inclusion of this oversymplectic groupoid in the symplectic groupoid, in the ambient symplectic groupoid I started with, is a coisotropic embedding. So it's a subgroupoid, which is also a coisotropic submanifold. And so this, you see, gives rise to what we may call the groupoid coisotropic embedding problem. So given an oversymplectic groupoid, is there a symplectic groupoid where this oversymplectic groupoid embeds as a coisotropic subgroupoid? And similarly, we have the question of neighborhood equivalence. So if I have two groupoid coisotropic embeddings in the same symplectic, of the same oversymplectic groupoid, so I have an oversymplectic groupoid, two groupoid coisotropic embeddings, are these two groupoid isotropic embeddings related? Coisotropic embeddings, are they related through a diffeomorphism of the symplectic groupoid that maps a neighborhood of one to a neighborhood of the other, and which switches the embeddings? So this should be familiar to anyone who have seen the coisotropic embedding problem in symplectic geometry. And we'll come back to that. So we will see that an oversymplectic groupoid that satisfies the so-called partial split condition can always has a coisotropic embedding into some symplectic groupoid. That symplectic groupoid is constructed out of the kernel of the symplectic form, of the oversymplectic form, and the embedding is given by the zero section. Now, we will see that it's not true that every oversymplectic groupoid can be embedded on a symplectic groupoid. One example of oversymplectic groupoid that can always be embedded is a proper oversymplectic groupoid. And in fact, those proper oversymplectic groupoids, they satisfy this partial split condition that I will explain later. And the second theorem is the normal form for coisotropic embeddings that says that any groupoid coisotropic embedding is actually equivalent to this canonical or local normal form that is stated in the first result. And out of this, of course, you can state a groupoid coisotropic neighborhood theorem about relating any two coisotropic embeddings. So let me just remind a little bit, a brief history of smooth linearization. So I emphasize here that I'm talking about smooth linearization, not other types of linearizations that also exist, such as formal or analytic linearization. So the first results were for a fixed point, and it started with the classical paper of Alan Weinstein that that he stated the linearization problem, he explained the local form, and then he made some conjectures about linearization. So Kohn in '85 proved his famous linearization theorem, stating that if the isotropy Lie algebra at the fixed point is compact semi-simple, then you can linearize. So that used the Nash-Moser technique. Now, much later, Monnier and Zung, they discussed something more general than normal forms called the Lévy decomposition. And out of that, they obtained a more general linearization result, a slightly more general linearization result than Kohn, saying that if you have a Lie algebra, which is a direct sum of a compact semi-simple and an abelian Lie algebra, then you can linearize. Again, their work used Nash-Moser. And later in 2011, Marius and myself, we gave a geometric proof of Kohn's theorem. Then for a symplectic leaf, this goes back to the work of Vorobiev. He was the first person to give a first order local model. And he also gave some results about the neighborhood equivalence around symplectic leaves. And then in 2012, Kreinik and Marcoux, they proved the linearization theorem for symplectic leaves. And this proof involves a geometric proof that extends the argument that Marius and myself gave in the case of fixed points. And finally, the most general result, as I have already mentioned before, was by Marcoux, and it was about rigidity around general Poisson submanifolds. So the linearization result that I stated before includes all these results as the special cases. It implies also the Marcoux result, but, so there is a but, which I will come back at the very end. And it's related with the way it's proved. All right, so this talk will be basically divided into three parts. The first part, I will try to explain these first order data and what are these jets of Poisson structures along a submanifold. Then we'll go to the global theory and discuss these coisotropic embeddings, the groupoid coisotropic embeddings. And from that, we will deduce our local models for Poisson submanifolds, and we'll come back to the local theory, discuss the existence of local models and these linearization theorem. So throughout the talk, this is my notation for a cotangent Lie algebroid. It's the usual notation. So we have this bracket on one forms and the pi sharp map that maps covectors to tangent vectors. And I'd like to start with a very classical result characterizing Poisson structures in terms of Lie algebroids. So to give a Poisson structure on a manifold is exactly the same thing as giving a Lie algebroid structure on the cotangent bundle, for which the anchor is skew-symmetric and the bracket of closed one forms is a closed one form. Now, nowadays, we state this in a slightly different way. We state that it's equivalent to give a Poisson structure on a manifold and to give a Lie algebroid structure on the cotangent bundle, for which the identity is a closed infinitesimal multiplicative two form. So infinitesimal multiplicative two forms are the infinitesimal analogs of multiplicative two forms on a groupoid. When you write this down explicitly, it sounds a little bit weird, but that's what it is. So a closed infinitesimal multiplicative two form is just a map from the algebroid to the cotangent bundle that satisfies two conditions. The first condition is a type of skew-symmetric condition, relating that map with the anchor. And the second condition explains what that map does to the Lie bracket on one forms. So I already noticed that I'm not obeying my notation. There should be a pi there in the bracket of the one forms. Now, the observation is that this classical result is really a result about jets of bivector fields. And I want to discuss that because then I want to inspire from that and extract from that the case of jets along some manifolds. So suppose I have a bundle, a vector bundle, say, and I take this first jet bundle. So that will be my notation for the jets of a bundle. And in the case where this bundle is the tangent bundle to the manifolds, and I start taking exterior powers of the tangent bundle, when I form the first jet, the Skelton bracket induces my bracket on the jets of sections, or sections of the jet space, I should say. And it's just characterized by the property that on holonomic jets, it is the jet of the bracket. Now, you may ask, if I have a jet which is not holonomic, what does it mean for the bracket with itself to be 0? Now, in this case, I'm asking for a jet with the second exterior power. So you can think that this is almost a Poisson structure, but it's not a Poisson structure because it's not holonomic. Well, the question is, the answer to this is the following. So such jets are the same thing as Lie algebroid structures for which the anchor is symmetric. So this is the first condition that appears in the classical theorem. What about the second condition? Well, that corresponds exactly to the holonomic jets, which are Poisson structures. So Poisson structures corresponds to Lie algebroids for which the identity is a closed IM2 form, or if you want to think in terms of jets, they correspond to these jets that are holonomic. So this is what we should keep in mind for the next discussion for some manifolds. Now, if you want to, I don't think I should insist on the proof of this, but the proof of this is simply because there is an embedding from the jets of the exterior power of the tangent bundle into the derivations of the cotangent bundle. And if you remember that algebraic structures are the same thing as a derivation whose bracket with itself is 0, then this result follows. And you have to observe another thing is that the image of this map is exactly the derivations whose symbol is skew-symmetric in some sense. Well, you have access to the slides, so if this part, I will just go over the proof without discussing it, and later, if you want, you can come back and take a look at the proof. All right, but as I was saying, I want to look at some manifolds, and so I will use the following notation. So if I have a closed submanifold, I will denote by these multi-vector fields whose restriction to the submanifold gives me a multi-vector field on the submanifold. So you may say multi-vector fields tangent to the submanifold. That will be my notation. I will put a subscript S in the space of multi-vector fields. All right, now, if I take the jet bundle of my some wedge power of Tm, I can restrict it to S, and I get a bundle over S. And inside this bundle, I have the jets for which the base of a jet is still a multi-vector field. Well, in this case, just a multi-vector because I'm taking it point-wise, not sections. So for which the base takes values in the wedge of Ts. So that's my notation, J1S of the wedge power of Tm. By the way, if you get lost in this discussion, I will make a summary at the end with all that you need to know. So this bundle comes with two projections. It comes with a projection to the jets of the wedge of Ts, and of course it comes to the projection to its base, which is the wedge of Ts. It also comes with a graded Lie bracket on its sections induced from the usual Skelton bracket. And finally, we were going to call a section of this jet space holonomic if this section is the jet of multi-vector field tangent to S. So this, of course, only involves the germ of that multi-vector field around S. So that's my notation for the holonomic sections of that jet space. And now, that projection I had before, of course, gives me a projection at the level of holonomic sections. And what does that give? So that projection gives me a map from multi-vector fields tangent to S to holonomic jets. And it has a base, which are just ordinary multi-vector fields. So this is at the level of sections. And this map is surjective. So this, in fact, gives you another way of thinking of these jets. These jets are really just multi-vector fields tangent to S, where I identify multi-vector fields which differs by the square of some function that vanishes along S. Well, I really have to take the ideal, but you see the point. All right, so jets can be thought as some equivalence classes of multi-vector fields where I identify multi-vector fields which differ by some multi-vector field that vanishes to second order along S. Now you may ask, what is the geometric meaning of a section of this jet bundle which satisfies this bracket with itself being 0? Well, the answer is pretty simple. What it means is a Lie algebraic structure on the restricted tangent bundle to S for which the first condition of being an IM form holds. So the skew symmetric condition between anchor and IM form. And moreover, these holonomic jets, they correspond to Lie algebraics for, sorry. So I didn't, so the IM form here is simply, so before we had the identity, when we had the whole tangent bundle, and here the IM form is going to be just a restriction from the restricted cotangent bundle of M to S to the cotangent bundle to S, just the restricting multi-vector fields to TS. So as I was saying, jets for which the bracket with itself vanish, they correspond to Lie algebraic structures on these restricted tangent bundle, which satisfy the first condition of IM form. And the holonomic jets corresponds to jets which satisfy both conditions. So for which this restriction map is a closed IM2 form. And again, the proof is the same thing, just obtained by restricting the previous map that we had in the situation where we didn't have a submanifold. All right, so this is the first conclusion. We should think of first order jets of a Poisson structure along S as holonomic jets for which the bracket with itself is 0. But by this proposition, we have a different way of looking at them. We can think of first order jets as multi-vector fields tangent to S, whose Schouten bracket doesn't vanish, but it vanishes to second order along S. And where I identify any two such multi-vector fields which differ by a multi-vector field which vanish to second order along S. Now, that's...
Why do you call it holomorphic?
Excuse me?
Why do you call this thing holonomic?
Because you see here that they are actually represented by multi-vector fields along S. And that's the only notion that you can make, the only sense you can make of holonomic here is that. But so we have this first characterization, and we have this other characterization that looks much simpler, which is simply saying, or at least to say it, but not to work, which is this a Lie algebraic structure on the restricted cotangent bundle for which this restriction is a closed IM2 form. And we'll have to jump between these two characterizations. And the final thing that you have to remember is that we have this map that takes germs of Poisson structures along S to these jets along S. And this map comes with projections to the Poisson structures on S. And these things in this slide is the only thing you actually need to remember from this discussion. So let's do an example. So let's take R3. Let's take the XY plane as the submanifold. And let's take a bivector, which is given by the formula I'm giving there. So z dx dy, so the bracket of x and y is z, and the bracket of x and z is x times z. So this is just a bivector, and now I claim that this represents a first order jet. So what do I need to check to see that it represents a first order jet? Well, I need to check that the Scouten bracket with itself vanishes to second order along S. And in fact, if I compute the Scouten bracket with itself, I see that this is z squared times the volume Scouten, the volume by 3 vector. So this indeed vanishes to second order along S. So that represents a first order jet. Now, the second claim, and this may be a little bit unexpected, is that this first order jet cannot be realized as a Poisson structure, as a germ of a Poisson structure. Well, for that, you need to compute things. So you look for all possible multi-vector fields whose first order jet coincides with this one. And you see that they take this form after some computations, and then you compute its Scouten bracket, and you see that its Scouten bracket never vanishes. So this first order jet is not realized as a jet of a Poisson structure, of a germ of a Poisson structure that has S as a submanifold. But now I can give you a little bit more precise versions of our problems. So we have this diagram, and what does it mean, a first order local model? Well, it's really a first order local model for a class of jets. If I have a class of jets, a first order local model is giving a splitting of this J1 map. Why is that? Well, because if I start with a Poisson structure that has S as a submanifold, and if its first jet takes values in this class, and if I apply my splitting, I will get a new Poisson structure which has S as a Poisson submanifold and which has the same first order jet. And so you see that splittings allow you to produce in a canonical way a linear, you may want to call it, Poisson structure along S, something that only depends on the first order data. So that's a very precise notion of what is a first order local model for a class of jets. And so our first theorem states that if I take the class satisfying the mysterious partial split condition, they admit such first order local model. So there is a splitting. And the normal form problem, what does it state in this language? So if I have a local model, so if I have a splitting, I will call it a local normal form if given any, once I fix an element in this class, a jet in this class, any other Poisson structure, or any Poisson structure whose first jet coincides with tau, it's locally isomorphic to the linear model that I obtained from the splitting. So this makes a very precise statement of what is a local normal form. So you can actually decide whether local normal forms exist or not in principle. And so our second theorem, the linearization theorem, says that if I take the class of jets for which remember, a jet can be represented by an algebraic structure on the restricted cotangent bundle. And so the assumption is that this restricted cotangent bundle integrates to a compact Lie groupoid whose source fibers have trivial second rank cohomology. So under that assumption, this class C satisfies this partial split condition, so it meets a local model, and that local model is a local normal form. Okay, again, I'll come back to this. So we are going incremental. All right, so that's the end of the first part of the talk, which was about jets and making precise what is first order local data, what are local forms, and what are these local normal forms, and the precise versions of our results. So now I'm going to go to the global theory. And so here is, again, something I already mentioned, which is a definition of an oversymplectic groupoid. So it's a groupoid. I have a closed multiplicative two-form, and the kernel of this two-form is controlled, meaning it's contained in the isotropy, or in the tangent to the isotropy, if you prefer. So from this paper of Burstein, Kreinig, Weinstein, and Zhu, there is a various characterizations of oversymplectic groupoids, and one of them is the following. To have an oversymplectic structure, so if I start with a groupoid where I fix a closed multiplicative 2 form, then that satisfies this condition on the kernel, if and only if there exists a Poisson structure on the base of the groupoid that makes the target a forward Dirac map. So in other words, you can think that oversymplectic groupoids are exactly those groupoids for which this closed multiplicative 2 form induces a Poisson structure on the base. Moreover, if this holds, then you can show that the kernel has constant rank. It's equal to the dimension of G minus twice the dimension of the base. And then the orbits of the groupoids, if I'm assuming groupoids are source connected, the orbits of the groupoid coincide with the symplectic leaves of the Poisson structure on the base. So this gives you a bit more of a geometric insight of oversymplectic groupoids. And why do they call them oversymplectic groupoids? Well, because what happens if you factor out the kernel of the form? So if you assume that the kernel defines a simple foliation, so the kernel is an integrable distribution because the form is closed and has constant rank. If this foliation is simple, if it has a smooth leaf space, then what you get on the leaf space is a symplectic structure, of course, because you factor out the kernel. The form descends, you get a multiplicative form which is non-degenerate, so you get a symplectic groupoid. And that symplectic groupoid integrates the Poisson manifold on the base. So that's the origin of the name oversymplectic. And why are oversymplectic groupoids relevant for us? Well, the first thing I already mentioned, if I start with a symplectic groupoid and I fix a Poisson submanifold on the base, then the restriction is an oversymplectic groupoid and it's coisotropically embedded in the symplectic groupoid. Conversely, if I start with a coisotropic embedding of an oversymplectic groupoid, the embedding of the units is a Poisson map. Remember, we just explained that an oversymplectic groupoid has a Poisson structure on the base. And so if I start with an embedding of this oversymplectic groupoid at the level of the units, I will get a Poisson submanifold. I'll get a Poisson map. And in these statements, if you assume that the submanifolds are closed, then the submanifold is closed, then the corresponding embeddings are closed. And moreover, the submanifold is saturated. Again, because my assumption is that the source fibers are connected. And therefore, you can think that this groupoid is actually the restriction of G to S always. So from now on, I will not make distinctions between GS and the restriction of G to S whenever I have a coisotropic embedding, because we are talking about closed submanifolds. So what happens at infinitesimal level with oversymplectic groupoids? Well, oversymplectic groupoids, they just correspond to algebroids for which the corresponding, so a multiplicative 2 form, a closed multiplicative 2 form on the groupoid induces a closed IM2 form. And the condition of being oversymplectic translates at infinitesimal level to this closed IM2 form being subjective. Simply that. So you are starting to see the relevance for us of these because that's exactly what we had for jets of Poisson structures along S. We had an algebroid for which we had a surjective closed IM2 form, this restriction map. And of course, this is a one-to-one correspondence provided the source is simply connected. The source fibers are simply connected. So if I give now an oversymplectic groupoid integrating my algebroid with a surjective closed IM2 form, and if I have a coisotropic embedding of this oversymplectic groupoid in a symplectic groupoid, I already mentioned that I have a Poisson embedding at the level of units. But moreover, I also get an isomorphism between the algebroid and the restricted cotangent bundle along S, which identifies my IM2 form with this canonical IM2 form restriction. So this new S, remember, on here is the restriction, the natural restriction to the cotangent bundle to S. So what does that mean? It means that whenever I'm in this situation, I actually have a solution. If I can find a coisotropic embedding of an oversymplectic groupoid integrating my first jet, I get a solution to the realization problem. I can find a Poisson structure whose first jet is tau. This is why this is relevant for the infinitesimal problem, for the normal form problem for Poisson structures. So here is a summary of this discussion. So I have symplectic groupoids. I have a saturated submanifolds. So that will be a Poisson submanifold on the base. I can restrict along S. I will get an oversymplectic groupoid over S. And there are maps under good conditions to symplectic groupoids over S. Remember that we needed that the kernel of omega S be a simple foliation. And a coisotropic embedding is a section of this restriction map. And now this is really just a version, this is just a groupoid version of the diagram that we saw before at the level of jets. And really this is all you have to remember. So unfortunately, I don't know how to make this, like making a little corner in my screen that would give you this throughout the rest of the talk. So let me give you an example. So this example is really about a class of examples. Is how are transitive, what are transitive oversymplectic groupoids? Well, they're very simple to describe. Transitive oversymplectic groupoids are given by specifying a principal bundle, which has a symplectic structure on the base. Now, by the standard gauge construction out of the principal bundle, we get a transitive symplectic group, transitive groupoid. And I can put on this transitive groupoid an oversymplectic structure by taking the usual construction where we take, we pull back the symplectic form by the two projections, and I get the basic form. So I have this is a symplectic form. It's a close to form here, which is multiplicative. It's basic, so it descends to a closed multiplicative form on my groupoid, and it satisfies the kernel condition. So this is a transitive oversymplectic groupoid, and in fact, it's very easy to see that every transitive oversymplectic groupoid arises in this way. So if you ever have seen local normal forms or local forms for symplectic leaves of Poisson manifolds, this should ring a bell. Now, this transitive oversymplectic groupoids always have a coisotropic embedding in a symplectic groupoid, and you can be very explicit about it. So the groupoid is obtained by taking 2 copies of my principal bundle, crossing it with the Lie algebra of my group. I act diagonal and I take the quotient, and that induces a groupoid that integrates the gauge groupoid. Forget about what I said something wrong. So this gives you a groupoid, and this groupoid comes with a symplectic structure, and it's a symplectic groupoid, and the canonical embedding of GS in here is a coisotropic embedding. Now, here is an example which has no coisotropic embedding. Well, remember we had this example of a first jet who was not realized as the jet of a Poisson structure. So let's just integrate that. And you can actually integrate that very explicit. And you obtain an oversymplectic groupoid. So what I'm doing is I'm integrating T star S and tau. For tau, J1 of pi, J1s of pi, this pi here. So if I integrate that, you have some fun and you find out that the integration is a bundle of groups. It's a bundle of groups over R2. Each fiber is a three-dimensional solvable group that it's varying only with the x coordinate in R2. And the multiplication is the multiplication that I'm giving there. At x equals 0, it becomes a billion, but for x different from 0 is a solvable three-dimensional group that is changing with x. And you also get the multiplicative closed 2 form that I wrote there explicitly by integrating that tau. And this is a coisotropic, it's an oversymplectic groupoid, but it cannot have any coisotropic embedding, because if this had a coisotropic embedding, by what we have just seen, I would get a Poisson structure on the base of the symplectic groupoid, which would extend this first order jet. And that's, we already know it's not possible.
But can you see directly?
Yes, you can also see that directly. Do you want to think about it? Or do you want me to tell you why?
Okay.
Well, maybe by the, ask me that at the end of the talk. Maybe you'll find it yourself by the end of the talk. Now, so this is a bundle of groups. You may think, oh, maybe all bundles of groups, oversymplectic groupoids, which are bundle of groups, are not they do not have coisotropic embeddings. But that's clearly not true, because you can take a Poisson symplectic groupoid, restrict to a Poisson submanifold, which consists of zeros of the Poisson structure, and that gives you a bundle of groups, which is coisotropically embedded. So there are many examples of oversymplectic bundles of Lie groups that admit coisotropic embeddings. Okay, maybe this is actually a good point to stop, because we are supposed to stop after 45 minutes, right? And I think this is probably a good point to stop. So we can, okay. I just saw some comments that it was too late for coffee in some places in the world.
A very nice background, by the way.
Oh, I'm out here in the main quad of the campus.
Yeah, it's
looks like
beautiful.
It looks like a CNN show.
Okay, so let's start again. It's 12:10. Please continue.
All right. Okay. So this was I just left the diagram here so people could stare at it. Of course, they have access to the slides, so they can always go back to the diagram. And so let's move forward to the place where we stopped. So we had an example transitive where we always had a coisotropic embedding, and then I gave you this example which had no coisotropic embedding. So at this point, you may wonder, well, wait. If you remember your symplectic geometry, if I have a coisotropic submanifold, I can always coisotropically embed it in a symplectic manifold. So what's going on? Why can't we apply Gotay's coisotropic embedding theorem here? So maybe I should recall just fastly what is Gotay's coisotropic. So I have a pre-symplectic manifold. So that means I have just a closed 2 form with constant rank. And then Gotay's provides a canonical coisotropic embedding. It's into the bundle obtained by taking the dual of the kernel of the form. And that bundle comes equipped with a symplectic form, which is obtained by pulling back along the projection from, so here I have the kernel of omega c, I have its dual bundle, it's a bundle over c, so this is the projection. So I have my form on c, I can pull it up via the projection, and provided I choose a splitting of the cotangent bundle of C, or equivalently of the tangent bundle of C relative to the kernel of omega or to the dual of the kernel of omega, I can also pull back the canonical symplectic form on the cotangent bundle of C via the inclusion given by this splitting. And this sum is a 2 form. It's non-degenerate on a neighborhood of the 0 section. So I get my symplectic manifold, and the 0 section is a coisotropic embedding. I'm not going to go through the proof of this, but it's useful to recall that what is going on when I have a coisotropic embedding. Well, if I have a coisotropic, so I think I jumped here something, but okay, never mind. So Gotes also says that any coisotropic embedding is equivalent to this embedding, to this canonical coisotropic embedding. And the reason is simply because the symplectic form on the ambient manifold, so here C is being coisotropically embedded in a manifold X omega. And the symplectic form gives me, by pushing down to the dual of the kernel, gives me a canonical isomorphism with the normal bundle to C, and then I fix a tubular neighborhood to X. And the point is I can use Moser to fix this tubular neighborhood so that this becomes a coisotropic embedding. So this here, it's good to keep in mind this identification. So, all right, we have this. Why don't we just apply this to our oversymplectic groupoid, GS omega S? After all, this is just a principletic manifold for which the form has constant rank. Well, there are two issues. One is this bundle an oversymplectic groupoid? Is this bundle a groupoid? The second issue is this bundle, does it have, it has a symplectic structure, but can I choose, if it is a groupoid, can I choose the symplectic structure to be compatible with the groupoid structure so that I get a symplectic groupoid? So let's discuss both these aspects. And for that, I need the following fact. Suppose I start with an oversymplectic groupoid. Remember that has an algebroid for which I have the surjective closed IM2 form. I can look at the kernel of the symplectic form along the identity section. So that's this. That gives me a subbundle of the tangent bundle to the groupoid. But it is contained, because of this is an oversymplectic groupoid, it's containing the tangent to the isotropy. And in fact, this kernel is also the kernel of the IM2 form. So what does that mean? Well, because this is contained in the tangent to the isotropy, you can check that indeed the groupoid acts on this bundle. So this bundle comes with a representation of the groupoid. So GX acts on this K. And now the kernel, because the form is multiplicative, the kernel of the form is in fact a subgroupoid of the tangent groupoid of GS. So whenever I have a groupoid, I have the tangent groupoid, which is a groupoid over the tangent of the base. And because this form is multiplicative, this is a subgroupoid. And in fact, this groupoid is canonically isomorphic to the groupoid that I obtain by taking the extension of GS by this action on K. So this is the groupoid multiplication, where here you see that I'm using the action of an arrow on an element of K. So if I look at the kernel of the oversymplectic structure, I have this diagram. So on the one hand, it's a subbundle of the tangent groupoid, but this tangent groupoid is a groupoid over the tangent of S, but it's also what's called a VB groupoid from vector bundle. So in this diagram, the back square are all vector bundles over the front square. And so in order to see the base of the kernel of S as a vector bundle over S, I think of S as the zero section of the tangent bundle to S. So this is the trivial bundle over S. So this is very important. We really should think of the kernel of the form. Remember, we are interested in the dual of the kernel of the form. That's from Gotes, that's where I should have my coisotropic embedding. So the kernel of the form, it's naturally a VB groupoid. Now for VB groupoids, there is a dualization procedure. Remember, we're interested in the dual of the kernel. So here is again the diagram, and I'm going to dualize it. And when I dualize it, this is what I get. So now the dual is actually a Lie groupoid over the dual of these representation. And the cotangent bundle of the groupoid is a groupoid over the dual of the Lie algebroid of my oversymplectic groupoid. And again, this is a VB groupoid, meaning these are all vector bundles over the front square. So this is the dualization procedure. Forget about the dash arrow for now. So what do we conclude from here? Well, we conclude that the kernel of the dual of the kernel of the form has a groupoid structure. We conclude that the zero section is embedded in this groupoid as a closed subgroupoid. And we also conclude, and now I recall back the Gotay's construction, that if I have a coisotropic embedding, I'll get a groupoid isomorphism between this dual of the kernel and the normal bundle to GS. But because the form is multiplicative, this arrow here is a groupoid isomorphism. That's actually equivalent to the form being multiplicative. And the projections going down are groupoid morphism. So this isomorphism is really a groupoid isomorphism. So what is this saying? Well, whenever I have a groupoid and I have a subgroupoid over a saturated submanifolds, the normal bundle to the groupoid, to the subgroupoid, is a model for what's called the linearization of the groupoid along the subgroupoid. So this is saying that as a groupoid, the dual of the kernel is canonically isomorphic to the linearization of G along GS. So this shows that we are in the right track, that we want to use this as our local model. And this is saying that from the groupoid perspective, we have the right local model. This local model is indeed the linearization of my groupoid along the subgroupoid whenever I have a coisotropic embedding. So from the groupoid perspective, this is very nice. But now what about the symplectic structure, which actually was what guided us towards this model? Well, for the symplectic structure, remember that Gotay needed the choice of a splitting. So we cannot choose an arbitrary splitting, because if we choose an arbitrary splitting, the form that we are going to get has no connection with the groupoid structure. So we should choose as a splitting a VB subgroupoid of the cotangent bundle. And this may not be possible. So finally, I can start lifting a bit this partial split condition mystery. So what is a partial split oversymplectic groupoid? Well, it's just an oversymplectic groupoid for which I can choose such a VB subgroupoid. In other words, it's a oversymplectic groupoid which admits a VB groupoid morphism, so a groupoid morphism from the dual of the kernel to the cotangent bundle of my groupoid, and which is also a vector bundle map, and which splits the canonical projection that I have from the cotangent bundle into the dual of the kernel. This is the dual of the inclusion of the kernel on the tangent bundle. So that's what a partial split oversymplectic groupoid is. It's one that admits such groupoid morphism, and one calls such a splitting a partial splitting. And again, this may exist or may not. So what is the symplectic groupoid law? Excuse me?
Can you also describe the dual of it?
The dual of?
Is there a dual picture of partial splitting?
Yes, yes. Maybe we'll come back to that. So a symplectic groupoid local model for my oversymplectic groupoid, what is it? Well, I have it whenever I have a partially split oversymplectic groupoid. So one for which there exists such a splitting. And as a groupoid is simply the kernel of omega S, or if you prefer, is this action groupoid for the action of the groupoid on the kernel of my form along the units. The symplectic form is just obtained from the Gautier's construction. So it's taking again the projection from the kernel of omega S, the dual. That's a bundle over GS. So that's the projection. I pull back my form, and then I add the pullback under my splitting of the canonical symplectic form on the dual. So this form, omega 0, is multiplicative. It's closed because both these maps, the projection and the theta, are groupoid morphisms, and the pullback of multiplicative forms along groupoid morphisms is multiplicative. Of course, it preserves closeness of forms. And the canonical symplectic form on the dual of the cotangent groupoid, on the cotangent groupoid, is a multiplicative form. Now, this form may not be non-degenerate everywhere, but it's non-degenerate in a groupoid neighborhood of the zero section. So on a groupoid neighborhood of the zero section, I do get a symplectic groupoid. In general, I will get a groupoid with a multiplicative closed to form everywhere. So let's come back to our example of transitive oversymplectic groupoids. So transitive oversymplectic groupoids, they always take the form of a gauge groupoid for a principal bundle where the base is a symplectic manifold. So this is the construction we saw before. And the first remark is that these transitive oversymplectic groupoids are always partial split. And in fact, the partial splittings are just the same thing. So choosing a partial splitting is just the same thing as choosing a principal bundle connection for the principal bundle. There is a one-to-one correspondence between partial splittings and principal bundle connections. So we can form the groupoid local model according to this definition. And what do we get? Well, the resulting groupoid local model is exactly the groupoid, the symplectic groupoid that I gave you before. So let's discuss a little bit this local model. So the first question is about uniqueness, because we were choosing a partial splitting. So how much does this depend on partial splittings? Well, before that, let's observe that this symplectic form, or well, it's close to form, it's only symplectic on the neighborhood of the zero section. It has two terms. One term is a constant term, the other term is linear. And what is the origin of these names? Well, if I take multiplication along the fibers, I'm calling a form constant if it's preserved by multiplication, and I'm calling a form linear if it's scaled by t. So this also makes sense of the fact that this local model that we are constructing, even from the symplectic point of view, is really a linear local model. The form is a constant plus a linear term. Now, a fact is that if you have a linear closed multiplicative two form, it's always exact, and the primitive is also linear multiplicative. So using that and a simple Moser argument, you see that local models are unique in the sense that if I choose two partial splittings and I construct their forms, I'm going to find a local groupoid automorphism which fixes the zero section and which pulls back one form to the other. This is just an ordinary Moser argument. The only thing we need to use is this basic fact that linear closed multiplicative two forms are exact. Why is that true? Well, that's true because if you take the user Euler vector field is multiplicative, and contraction of a multiplicative form by a multiplicative, by the Euler vector field, by a multiplicative vector field is multiplicative. And if it's linear, the contraction is linear. So this is about the answer, the question that Marius was asking. Can we think of these partial splits in different ways? So remember, a partial split was given as this map, this theta, big theta, which was given as, so let me go back. It was given as a map from the dual of the kernel to the tangent of the groupoid. Now, there are other ways of codifying this map. We can also codify this map via a linear infinitesimal multiplicative, sorry, not infinitesimal, linear multiplicative closed two form on this groupoid, which has further the property that along the identity section, it restricts to the canonical form on this subbundle that we have along the identity section. This is in TS. So that's a different way of giving this partial split. And still a different way of giving this partial split is to give a multiplicative form which has with coefficients in this representation, and which has the property that along the identity section, the restriction to K is the identity. So these are different ways of codifying the partial split condition, and they are useful whenever you are dealing with examples, trying to show, say, if some example is partial split, has a splitting. Now, all these conditions that I have here are linear in some sense. There is a more geometric condition of being partial split. And the geometric condition is simply that this groupoid local model that we have admits a symplectic form, which is, well, at least non-degenerate in the neighborhood of a closed multiplicative form, which is non-degenerate in the neighborhood of GS. Now, no conditions on linearity or anything, and which restricts along S to the form that we have on the oversymplectic groupoid. So this is saying what? This is saying that in general, my linear model is not a symplectic groupoid. If it is a symplectic groupoid, I get that it's partially split. That's what this is saying. So the partial splitting condition is really the right condition to put for the local model to be what we want, a symplectic groupoid. Well, let me not go through how you prove this, but well, maybe I can say something. So basically, the point is that if you have this condition, when you look at the limit of the pullback of the form along T, T goes to 0, you're going to get the projection, the pullback of the projection of omega S. And so here, this thing goes to 0. So if I again pull it back by nt and now divide by t, this has a limit, which is a form that satisfies this condition here. And so whenever I have my nonlinear form, I get the linear form. So a very important class of oversymplectic groupoids that are partially split. So we already saw that transitive oversymplectic groupoids are partially split. Another class that it's partially split is the oversymplectic groupoids that are S proper, that are source proper. And the proof of that requires some work. You have to use Morit equivalence to a local model, blah, 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 and use some of these conditions, or one of these alternative conditions, characterizations of partially split. So finally, we come to the groupoid coisotropic neighborhood theorem. So the first result in that direction is if I start with a symplectic groupoid, which is invariantly linearizable around a saturated submanifold, then it is the restriction of that groupoid to submanifold is partially split. So we have a local model, and this coisotropic embedding is going to be isomorphic to the coisotropic embedding on the symplectic groupoid local model. So note that there is no properness assumption here, but we have this invariantly linearizable condition. So what does that mean? What that means is that around this saturated submanifold, my symplectic groupoid is isomorphic as a groupoid to the linearization of the groupoids along this saturated submanifold in some saturated neighborhood. So message is, if I can linearize the groupoid, I can linearize the symplectic groupoid. That's what this is saying. But of course, if we are under S-proper symplectic groupoids, those are invariantly linearizable, and therefore those are locally isomorphic to the linear model. Okay, so that's the end of the second part. The second part was the global picture. And now what we want to do, we want to go back to the infinitesimal picture, to the level of Poisson manifolds and Poisson submanifolds. So the philosophical principle here is that one should think of Poisson geometry as infinitesimal multiplicative symplectic geometry. Recall the first result of the lecture was this classical result saying that Poisson manifolds are the same thing as Lie algebraic structures on the cotangent bundle for which the identity is an infinitesimal multiplicative form. So this leads to a dictionary. And the dictionary, of course, the first step is Lie groupoids go to Lie algebroids. Multiplicative forms go to infinitesimal multiplicative forms. If they have coefficients, they go to infinitesimal multiplicative forms with coefficients. And the last thing that you should remember is that multiplicative vector fields go to Lie algebroid derivations. And this is important whenever you want to do Moser arguments at the infinitesimal level. You should use Lie algebroid derivations as your vector fields. Your flows are going to be flows of Lie algebroid derivations, which are certain Lie algebroid automorphisms. So here is the dictionary. When you apply these rules, this is what you get. So we already saw entries in this dictionary. So if I start with a symplectic groupoid, I apply this rule, what I get at infinitesimal level is a Poisson manifold or alternative cotangent bundle with an algebraic structure for which identity is a closed infinitesimal multiplicative form. If I have a saturated submanifold at infinitesimal level, I get the Poisson submanifold. If I have an oversymplectic groupoid at the infinitesimal level, I get this first order jet, which we can think as an algebraic structure on the restricted tangent bundle for which the restriction is a closed IM form. If I have a coisotropic embedding, I apply my rules, and what I get in the other side of the dictionary is a realization, is a Poisson structure that realizes my first order local data as a first order jet of that Poisson structure. And now we want to know what are the local form at the infinitesimal level for a Poisson submanifold. Well, we apply the dictionary. So if I start with a partial splitting at the groupoid level, I'm going to get a partial splitting for the infinitesimal data. And the local form, the local normal form, the local form is going to give us a local model at the infinitesimal level. So we have to just to translate these things and find what are these red entries there. All right, so remember at the global level, when we look at the local model, we had groupoid aspects and symplectic geometry aspects. Here, same thing. At the local model infinitesimal level, we're going to have algebraic aspects and Poisson aspects, which are really infinitesimal multiplicative aspects, if you want. All right, so let's start with the algebraic level. So we start with our first order local data, and we have the kernel of my canonical IM form, and that is canonically a representation of my algebroid. So this is the infinitesimal version of what we saw at the groupoid level, where we had GS acting on this kernel. And here is simply, the representation is simply because, remember, this kernel is contained in the isotropy. This kernel, this bundle is contained in the kernel of rho. Therefore, I can use the bracket to get a representation. So we can form the action algebroid for this representation, and this is the infinitesimal analog of my model at the global level. This was the model at the global level, which now I can define without any integrability assumption, of course. And so the first proposition says that this action algebroid actually coincides with something that we know we have for algebroids. Whenever we have an algebroid, and that algebroid has a saturated submanifold, meaning a manifold made of orbits of the algebroid, I can linearize the algebroid along the saturated submanifold. And what I get is an action algebroid, which is the algebroid here that I'm writing on this side. And I have a canonical identification between what I get from these picture making the infinitesimal analog of the global picture, and my model is exactly what I should have. So this is the infinitesimal version of something we saw where we had kernel of omega s identified with the normal of GS at some point. Now, in general, so let's now turn to the Poisson geometric aspects. So just like in general, my local groupoid model at the global level was not a symplectic groupoid. Here, in general, my action, at the infinitesimal level, my action algebroid is not the cotangent algebroid of a Poisson structure. Okay. And what do we need? Well, we need a partial splitting condition. So a pair is going to be, so that, remember, this is the same, this is our tau, is like first order jet. It's called partially split if there exists an algebroid morphism which splits a natural projection. Now here, I'm really just taking advantage of the global picture to make everything infinitesimal. So at the global picture, we had the big theta was from GS action groupoid on KS with values in the cotangent bundle of the groupoid. And now this is the infinitesimal picture. And there is a natural projection. So here, we have to use the fact that the cotangent bundle of an algebroid is itself an algebroid over the dual of the algebroid that we started with. Now, that cotangent algebroid comes equipped with a canonical, non-degenerate, linear, closed IM2 form, which is just a very standard isomorphism in double geometry between the cotangent bundle of a vector bundle and the cotangent bundle of the dual vector bundle, which is known as the Tushevich isomorphism. So that, in our language, is just a linear closed IM2 form, which is non-degenerate because that's an isomorphism. So if I start with a first order jet, now, which is partially split, so I have my theta, I can construct my local model. And it's just what we did in the global side. So I have my bundle projection from this action algebroid to T star SM. On the base, I have nu S, which is an infinitesimal multiplicative 2, 4. This is an algebroid morphism, so I can pull back and I get my constant term, which is an infinitesimal multiplicative 2 form closed on the action algebroid. And using the splitting is also an algebroid morphism. I can pull back the canonical infinitesimal multiplicative 2 form that I have on the cotangent bundle of an algebroid, and I get the linear term. So that's the definition of the local model. Whenever I have a first jet which is partially split, I can form this local model. So this is an algebroid with an infinitesimal multiplicative 2 form. which is closed, and which is non-degenerate along the zero section. Since this is non-degenerate along the zero section, I can find the neighborhood of the zero section where it's non-degenerate. And on that neighborhood, I find my local model Poisson structure. And this local model Poisson structure has the property that its first jet at S is the local data that we started with. So again, I'm just following what the global side is. Now, at the global side, I'm repeating here different characterizations that of the partial split condition. Each of these conditions give rise to an infinitesimal characterization of partial split for first jets. So this is what you get if you do the infinitesimal version of those conditions. Now, I know this is very fast, so I don't expect you that you are following that each of these conditions correspond to the other ones. The only reason I'm pointing this out is that it's very convenient to have alternative characterizations. And when you start dealing with examples, you have to use these alternative characterizations. So I have an example here where I look at the transitive version at the infinitesimal side. So suppose I have my first order data, and suppose the algebra is transitive. So rho is surjective. Well, then I can choose a splitting of the anchor. And if I choose a splitting of the anchor, I get immediately IM one form on my algebra with coefficients in this representation, which satisfies this extra condition that we need. And therefore, by this equivalence, this is always partially split. And so I can form the local model. And what do I get if I form the local model? By the recipe I just told you, well, we get what is called the Vorobiev local model. So in this way, you recover what the only local model around symplectic leaves that it's known in the literature, or the only general local model, that's Vorobiev local model. So there are a couple more things that we need to discuss. So first we need to discuss uniqueness of the local model. So suppose I start with first order data, which is partially split. I choose two splittings. Well, then there's going to be an algebraic automorphism. It's defined only around my S, so the zero section. And it pulls back one multiplicative form to the other multiplicative form. So it gives an isomorphism of the local models. And the proof of this is just the infinitesimal version of the proof of the global case. I wrote here a few lines. So again, every linear closed infinitesimal multiplicative two form is exact. The primitive is a linear infinitesimal multiplicative one form. So you build a path of infinitesimal multiplicative forms, starting at one local model and ending at the other local model. And now you have a path of infinitesimal multiplicative two forms. You go through the usual modes of process. The only thing you have to remember is that you have, you see, you're going to look for a family of Lie algebraic automorphisms that pulls back, say, nu t to nu zero. And the infinitesimal version of this family is a Lie algebraic derivation. That's the infinitesimal version of a multiplicative vector field. And so that's what you are looking for, is for a Lie algebraic derivation, and then you show that you can solve the cohomological equation and prove uniqueness of the local model. And finally, we have the linearization theorem. So suppose I'm giving you a first order jet of a Poisson structure. And suppose that this first order jet, which I can view as a Lie algebroid, is integrable by a compact Lie groupoid whose source fibers have trivial second rank cohomology. Then this first order jet is partially split, satisfies the partially split condition. And any Poisson structure that I choose that has this first same jet along S is locally isomorphic to the local model. And how do we prove this? Okay, so remember at the beginning, I stated the linearization theorem, and I stated as a corollary the rigidity theorem of Marcoux. So now I'm going to disappoint you a little bit because, sorry, here is the proof. So there are two proofs. One is a general proof about this result, and this is the so-called Nash-Moser proof because that's what the rigidity theorem of Marcoux uses. So first, since we are assuming that this algebroid integrates to an S-proper groupoid, and we know that S-proper groupoids are partially split, it follows that this algebroid is partially split. Therefore, by the rigidity theorem of Marcoux, we know that any Poisson manifold which has this first jet, any two Poisson manifolds we have the same first order jet, they are actually isomorphic. So we can apply that to conclude that if I give you any Poisson structure, it's going to be locally isomorphic to my local model. That's it. So we are actually using here Marcoux's result. So Marcoux, and when I stated it was a corollary, it's actually because it's equivalent to this result. And the proof that I'm giving here uses that result. Now there is something that you actually discover by doing this result that you don't discover from Marcoux. So from Marcoux, you cannot actually conclude that if you have a Poisson structure whose first order jet is satisfies these assumptions, that Poisson structure is integrable. Now this shows that it actually is integrable because the local form is integrable under these assumptions. Now, to maybe make you feel better about having listened for me for an hour and a half, here is another proof that it's independent of these, but where we need an extra condition. So assume that the integration is same assumptions, but furthermore, it's also source simply connected. Now, these were the assumptions that existed in the theorem of Kreinic and Marcoux about local model for symplectic leaves. And now, if we have this assumption, we can give a geometric proof of this theorem pretty much along the same lines. So it goes with two steps. The first is to show that a neighborhood of S is integrable by an S-proper symplectic groupoid. And the second step is to apply our groupoid coisotropic neighborhood theorem. So that's very nice, but the first step is actually not as trivial as you may think at first. So the first step uses three things. It uses the path space approach to integrability. It uses a result from the paper of Marius with myself about the geometric approach to cones linearization theorem, where we give the geometric proof of cones, which has a result about foliations, which is crucial to prove integrability. And that same result was already used, it's exactly the result was already used by Kreinic and Marcoux in the linearization around symplectic leaves. But you can use that result here for Poisson submanifolds to prove integrability. So actually, that's the result which I don't expect you to see. It's a rather technical result, but it's a really important result. Okay, I want to close with a final comment. The comment is the following. So at the beginning, when we had the jet discussion, we had this diagram that explained in a bit more precise way, what does it really mean to have a local model and a normal form, okay? And we described a local form, not a normal form, or the normal, for partially split local data, right? And under some conditions, it becomes a normal form. But it's not about being a normal form, it's just about having a local form. Now, this local form is not, I'm not claiming that for any first jet, that's the only local form that you can find. In fact, if you look in the case of bisymplectic manifolds, and if you look at the singular locus, it's a standard result that you have a local form around the singular locus. But that's a different kind of local normal form. So in fact, that's a different kind, and the reason is the following. So in our local form, remember, we always have underlying the local form a Poisson structure, which is the cotangent, for which the cotangent algebroid is an action algebroid. In the normal form for the singular locals of a B-symplectic manifold, the Poisson structure that you have in the normal form, its cotangent algebroid is not an action algebroid. So it's not of this type. So this is, I think, a bit intriguing. And it also makes you wonder, are there other kinds of local normal forms? And so I think I will stop here, and I thank you for your attention.
Okay, thanks, Rui.
Yeah.
Clapping, I'll clap on behalf of the muted participants. So for questions, the way that you should ask questions is to click on the participants icon at the bottom of your screen, and then raise your hand, and then Nikita will unmute you. So get ready with your questions, and I'll start off with one question. So in your, if you look at your slide, oh, actually your slides don't have numbers.
Yeah, these numbers in PDFs, they are actually concerned with the pauses, so it's not really a number on the slide. But
the slide that you have, the 3 conditions on the infinitesimal level for a partially split.
Sure.
I'm just wondering, like when you, yeah, that's right. So I'm wondering if there's one of these conditions which makes it possible to compute maybe cohomologically, for example, in the example that you gave at the beginning, that there's an obstruction to this partial splitting.
Maybe.
What kind of obstruction is it? Like, is it?
Well,
is it similar to curvature in the sense of?
It is. You can write an obstruction in that sense because this is an obstruction to existence of a splitting. So you know you can always have a splitting, and the splitting is, you want it to be an algebroid splitting, right? So there is a curvature equation that you can get out of that at infinitesimal level.
Okay.
But yeah, I haven't write down that down, and it may be actually a very good idea to write it down. Yes, I agree. Mm-hmm.
Okay, I'll open it up to the, there's 2 questions, so I'll mute myself and maybe Nikita can select the questions.
So, Rhea?
Hi, Rui.
Hi.
That's a silly question. What is a compact Lie groupoid?
A compact Lie groupoid is a Lie groupoid whose total space of arrows is compact. And by the way, I didn't say that, but whenever I say that the groupoid is compact or it is source proper, I assume that it's Hausdorff.
How does this get used exactly, the compactness?
So let's go back. So the compactness gets used in the Nash-Moser proof to make estimates. And in the geometric proof, it's used for stability in the sense of Reeb stability. So it's something that it's really important to have.
All right. Thank you.
Sure, you're welcome.
For your talk.
Thanks.
Marius? Marius, you need to unmute yourself.
Okay, do you hear me now?
Yes.
So the question was actually asked by Marco, but I want to add a comment. But it would be nice if the existence of a partial splitting would be equivalent to the vanishing of some cohomology class, or maybe some mapping cohomology, something of the nature, so that in the proper case, it is partially split because of the vanishing of the cohomology. So, Rui, do you think something like that could happen?
I think so. I think it's possible. I think it makes sense. I don't know if Jonut is listening to, and he may also have some feeling about that. So, but I agree. If we can do that, it would be really nice.
So I think this is something we tried quite a bit at the beginning, and it worked for some cases of Lie algebroids, like when the isotropies were abelian, or in some situations you could write it as a cohomological condition, but in general, there were
some of the things that we discussed at the beginning not so clear in my mind anymore. But anyway.
One consequence of the partial split condition is that, which is somehow very intriguing, is that the isotropy Lie algebras. So inside the isotropy Lie algebras, you have the conormal directions to the submanifolds, and those are ideals in general, and those will be all isomorphic if this partial split condition holds. That's what they're also different than what you would expect. So this is another obstruction.
Okay, Marco?
Another thing that I was wondering, but I think your comment at the end indicates the answer. So a very interesting class of normal forms around the Poisson submanifolds is that of elliptic Poisson structures that come from stable generalized complex geometry. So there's the normal form that Marco and Cavalcanti have. Just curious whether that fits in this picture. Just that your comment about B symplectic indicates that it may not.
It's 19 hours.
Rui?
Something is going wrong.
Sorry, my connection went down, and I lost sound.
And
too, I think now you have my sound.
Muted.
So we can
so
sort
the
of hear you.
elliptic, I think in the elliptic case, you also, the local model that you have is not going to be of this sort.
Okay.
Okay, Marco, do you want to ask your question?
Yes.
I think.
Yes. I was wondering about the case, like if you have a saturated submanifold, which is not a single symplectic leaf.
Yes.
Then what is this kappa? This K subalgebroid? How do you define it?
Kernel. So in the case, let me try to put back the share my. Okay, share. Still sharing. Well, for some reason, it's not sharing my iPad. But I think my connection is unstable. That's what this message is. So the answer is, in that case, it's the annihilation. So whenever you have the quotient bundle of M, you restrict to the submanifold S. The kappa is, well, the kappa is the annihilator of the tangent to S, which sits inside the quotient bundle to S. That's the kappa.
Right.
Right.
Okay, and so the integrability of T star sub S. How do we what's the how would you say the criterion goes for that integrability?
Well, that's that you apply the general integrability criteria for algebroids. Okay, I got it.
Okay, so there's nothing specific to this case. It's just that
not in general.
You appeal to the general.
Yeah. So in the transitive case, yeah.
Does anyone else have any questions?
Okay, so if there's no more questions, I just wanted to remind everyone that we will have another, the schedule is already set for the next couple of weeks. We have next week, Eckhard Meinrenken will be speaking. And then the week afterwards, it will be Eva Miranda. Thank you for agreeing to give those talks. And just to end today, let's thank Rui.
Marco, sorry, yeah, maybe on the schedule, actually, the schedule had been updated. So next week it is Eckhard Meinrenken, but I think the week after it will be Pavel Ettingov, and Eva will be speaking sometime in mid-May.
Ah, okay, great.
Yeah, but the schedule is on the website.
Okay, see everyone next week.
Okay.
Thanks again, Rui.
Thank you all. Thanks.
Thanks. Thank you, Rui.